The calculations required to simulate the universe exceed the universe itself. And this is not a philosophical opinion, but a mathematical consequence of the most fundamental limits in physics. The simulation hypothesis, popularized by Nick Bostrom and endorsed by figures like Elon Musk, claims we might live in a computer simulation. But physics proves this impossible. The Bekenstein bound, derived by Jacob Bekenstein in 1981, establishes that the maximum information content of any finite region of space is bounded by its energy and its radius. S is less than or equal to 2 pi k sub b Re over h bar c. The Bremermann limit, formulated by Hans Bremermann in 1962, establishes the maximum computational speed of any physical system, approximately 1.36 times 10 to the 50 bits per second per kilogram, derived directly from Einstein's mass-energy equivalence and the Heisenberg uncertainty principle. The Margolus-Levitin theorem, proved by Norman Margolus and Lev Levitin in 1998, establishes the quantum speed limit. No physical system can transition between distinguishable states faster than 2e over pi h-bar operations per second, where E is the system's total energy. And Seth Lloyd, applying all three limits to the entire observable universe, calculated in 2000 that the cosmos, treated as the ultimate computer, could have performed at most approximately 10 to the 120 elementary operations on approximately 10 to the 90 bits of information in its entire 13.8 billion year history. 10 to the 120 operations, 10 to the 90 bits. These are the absolute maximum, the theoretical ceiling, the most any physical system with the mass energy of the observable universe could compute if every particle were a processor and every interaction a calculation. And the computational cost of simulating even a small region of space, a single cubic metre of quantum vacuum at Planck scale resolution, exceeds this ceiling by orders of magnitude that defy comprehension. The universe cannot simulate itself. The universe cannot even simulate a fraction of itself. And the question of why a cosmos with such extraordinary computational structure exists at all, why the laws are mathematically precise, why the constants are fine-tuned, why information is bounded by elegant equations, is the question that computational physics raises but cannot answer. What follows is a forensic examination of the evidence. By the end of this video, you will understand the Bekenstein bound, the maximum information any region of space can contain. You will understand the Bremermann limit, the maximum speed at which any mass can process information. You will understand the Margolus-Levitin theorem, the quantum speed limit that sets an absolute ceiling on computation. You will understand Seth Lloyd's calculation, the most operations the observable universe could have performed since the Big Bang. You will understand why quantum chromodynamics, the theory of quarks and gluons, the strong nuclear force, is so computationally expensive that even the most powerful classical supercomputers cannot simulate real-time hadron collisions, and why even quantum computers face fundamental limitations. You will understand why the simulation hypothesis, the idea popularized by Nick Bostrom in 2003 that our universe is a computer simulation, fails not because of technological limitations, but because of the laws of physics themselves. You will understand why a 2025 paper by Krauss-Faizal and colleagues in the Journal of Holography Applications in Physics argued mathematically that the universe cannot be a simulation, that computation is not more fundamental than space-time, but embedded within it. And you will understand why the evidence, when examined honestly, points not to a simulated universe, not to a self-computing cosmos, not to an accidental configuration of matter and energy, but to an intelligent, powerful, eternal creator who configured the laws, set the constants, and brought into existence a universe whose computational structure testifies to the attributes of its maker. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us examine the evidence. The foundation of the argument is information, and the discovery that information is not abstract but physical, not metaphorical but measurable, not separate from matter and energy but encoded within them. Before the 20th century, information was considered a human concept, a property of messages, books, and communications, having nothing to do with physics. The 20th century destroyed that assumption. 3 discoveries by Shannon, Landauer, and Wheeler established that information is as physical as mass, as fundamental as energy, and as subject to the laws of thermodynamics as any particle or field. Claude Shannon, born 1916, died 2001, American mathematician and electrical engineer at Bell Labs and MIT, established the mathematical theory of information in 1948 with his paper, A Mathematical Theory of Communication. Shannon defined information entropy. H equals the negative sum of P sub I times the logarithm base 2 of P sub I, where P sub I is the probability of the ith outcome. This connects directly to von Neumann entropy in quantum systems, extending information theory into the quantum realm. Shannon's formula quantifies how much information is contained in a message, how many binary digits, bits, are needed to encode it, how much uncertainty it resolves, how much you learn by reading it. A fair coin flip has an entropy of exactly 1 bit. A message in English has approximately 1 to 1.5 bits per character. Because English is redundant, not every letter combination is equally likely. The formula transformed communication from an art into a science, enabling the design of error-correcting codes, data compression, and the entire digital revolution. Shannon's formula, however, has a deeper significance. It has the same mathematical form as Boltzmann's thermodynamic entropy. S equals K sub B times the natural logarithm of W. John von Neumann, one of the greatest mathematicians of the 20th century, reportedly advised Shannon to name his quantity entropy because nobody knows what entropy really is, so in a debate you will always have the advantage. The remark was witty, but the connection is not a coincidence. Both formulas count the same thing: the number of ways a system can be arranged while producing the same macroscopic appearance. Boltzmann's entropy counts molecular configurations. Shannon's entropy counts message configurations. Both measure missing information, the information about the microscopic state that the macroscopic description does not capture. Rolf Landauer, born 1927, died 1999, German-American physicist at IBM's Thomas J. Watson Research Center, took this connection from mathematical analogy to physical law. In 1961, Landauer demonstrated that information is physical, that erasing a bit of information is not merely a logical operation, but a thermodynamic process with a measurable physical cost. Landauer's principle states, erasing one bit of information must dissipate at least k sub bt times the natural logarithm of 2 in heat into the environment. K sub b is Boltzmann's constant, approximately 1.381 times 10 to the negative 23 joules per Kelvin. T is the temperature. At room temperature, approximately 300 Kelvin, the minimum energy dissipated per bit erased is approximately 2.87 times 10 to the negative 21 joules, approximately 0.018 electron volts. This was experimentally confirmed in 2012 by Antoine Beroux and colleagues, who measured the heat dissipated when erasing a single bit stored in the position of a colloidal particle trapped by a laser. The measured heat matched the Landauer bound to within experimental uncertainty. Landauer's principle has a devastating implication for computation. Every irreversible logical operation, every AND gate, every OR gate, every bit erasure, produces heat. Every computation that destroys information increases the entropy of the universe. Computation is not free. Computation is physical. And the thermodynamic cost of computation is not a technological limitation. It is a law of nature, as fundamental as the conservation of energy. Charles Bennett, born 1943, American physicist, also at IBM, extended Landauer's work by showing that logically reversible computation, computation that does not erase information, can, in principle, be performed with arbitrarily little energy. But reversible computation requires storing all intermediate results. The memory cost grows without bound. In practice, every real computer erases information, and every real computation produces entropy. John Archibald Wheeler, born 1911, died 2008, American theoretical physicist, colleague of Einstein at Princeton, doctoral advisor to Richard Feynman and Hugh Everett, the man who coined the terms black hole and wormhole, captured the physical nature of information in 3 words: it from bit. Wheeler proposed in the early 1990s that the physical universe is fundamentally informational, that every particle, every field, every interaction derives its function, its existence, its very reality from information. Yes or no answers to physical questions. The universe, in Wheeler's framing, is not a machine made of stuff. It is a structure made of information. Every measurement is a question posed to nature. Every physical event is an answer. And the totality of answers, the total information content of the universe, defines everything that exists. Wheeler's it from bit remains a philosophical proposal, not a proven theorem. But it captures a truth that the Bekenstein bound, the Bremermann limit, and the Margolus-Levitin theorem make precise. The universe has a finite, calculable information content, and a finite, calculable computational capacity. Information is not an abstraction layered on top of physics. Information is the substrate of physics, And that substrate, as we are about to see, is bounded. This sets the stage for the central question. If the universe is informational, how much information does it contain? And can any physical system, including the universe itself, compute enough to simulate that information? The answer to the first question comes from the Bekenstein bound, the most fundamental limit on information in the physical universe. Jacob Bekenstein, born 1947 in Mexico City, died 2015 in Helsinki, Israeli-American theoretical physicist, derived the bound in 1981, building on his earlier work on black hole thermodynamics. Bekenstein had shown in 1972 that black holes carry entropy, that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was a radical idea. It meant that a black hole, the densest object in the universe, stores its information on its surface, not in its interior. Stephen Hawking, working independently and initially in opposition to Bekenstein, completed the calculation in 1974, deriving the precise formula. S sub BH equals A over 4 in Planck units. A is the area of the event horizon. Each Planck area, approximately 2.6 times 10 to the negative 70 square meters, approximately 2.8 times 10 to the negative 69 square feet, encodes approximately 1 bit of information. This discovery laid the foundation for the holographic principle, the profound idea that all information in a volume can be encoded on its boundary. From this work, Bekenstein derived a more general bound, a limit on the maximum information content of any region of space, not just black holes. The Bekenstein bound states S is less than or equal to 2 pi k sub b r e over h bar c. S is the entropy, the maximum number of bits in natural units that the region can contain. K sub b is Boltzmann's constant, approximately 1.381 times 10 to the negative 23 joules per Kelvin. R is the radius of the bounding sphere, the size of the region. E is the total energy enclosed within the region. H bar is the reduced Planck constant, approximately 1.055 times 10 to the negative 34 joule seconds. C is the speed of light, approximately 299,792 kilometers per second, approximately 186,282 miles per second. In bits, the bound becomes I is less than or equal to 2 pi r e over h bar c times the natural logarithm of 2. The bound says something extraordinary. No finite region of space, no matter how dense, no matter how complex, no matter how cleverly engineered, can contain more than a specific, calculable number of bits of information. The information capacity is determined entirely by 2 quantities, the energy and the size. Double the energy, double the information capacity. Double the radius, double the information capacity. But the capacity is always finite, always bounded, always calculable. Let us make this concrete. Consider a sphere of radius 1 meter, approximately 3.28 feet, containing energy E. At the Bekenstein limit, the maximum information content is approximately 2.58 times 10 to the 43 bits per joule of energy enclosed. For a 1 kilogram mass, E approximately equals 9 times 10 to the 16 joules via E equals mc squared, in a 1 metre sphere, the bound gives approximately 2.3 times 10 to the 60 bits. This is an enormous number, but it is finite, it is calculable, and it is an absolute maximum. No physical process can exceed it. Now consider the observable universe. The observable universe has a radius of approximately 46.6 billion light-years, approximately 4.4 times 10 to the 26 meters. It contains approximately 1.46 times 10 to the 53 kilograms of baryonic matter, with a total mass energy of approximately 5 times 10 to the 69 joules, including dark energy. The Bekenstein bound for the observable universe gives a maximum information content of approximately 10 to the 90 bits. Including gravitational degrees of freedom, the information stored on cosmic horizons might raise this to approximately 10 to the 120 bits. But the key point is, the number is finite. The observable universe can contain at most approximately 10 to the 90 to 10 to the 120 bits of information. Imagine what this means visually. Every atom in the observable universe, approximately 10 to the 80 atoms, mostly hydrogen, filling a volume approximately 93 billion light-years across, every photon, every neutrino, every dark matter particle, every gravitational wave propagating through space-time, every quantum fluctuation in every field at every point in space, all of it together encodes at most approximately 10 to the 90 to 10 to the 120 bits. The universe is not infinite in its information content. It is not unlimited in its computational resources. It is bounded by the Bekenstein bound, by the laws of quantum mechanics and general relativity, by the finite energy and finite size of the observable cosmos. The implication for simulation is immediate and devastating. To simulate the universe, you need a computer with at least as many bits of memory as the universe contains. The Bekenstein bound says the universe contains at most approximately 10 to the 90 to 10 to the 120 bits. Where do you put the simulating computer? Inside the universe? Then the computer uses the universe's own information capacity, and there is no room left for the simulation. The computer is the universe, and the simulation is reality. Outside the universe? Then you have invoked something beyond the physical cosmos, something not bounded by the Bekenstein bound, not limited by the laws of physics, not subject to the constraints that govern every physical system. You have invoked, whether you intended to or not, a transcendent computational substrate. And a transcendent computational substrate is, in every meaningful sense, a creator by another name. The answer to the second question, how fast can a computer process information, comes from the Bremermann limit and the Margolus-Levitin theorem. These are not engineering constraints. They are not limitations of current technology. They are consequences of quantum mechanics and relativity, the two most fundamental and experimentally confirmed theories in all of physics. Hans Bremermann, born 1935, died 1993, German-American mathematician at the University of California, Berkeley, derived the Bremermann limit in 1962. The derivation is elegant and follows from two equations that every physics student learns in their first year. The first equation: Einstein's mass-energy equivalence, E equals mc squared. A system of mass m has energy E equals m times the speed of light squared. 1 kilogram of matter contains approximately 9 times 10 to the 16 joules, the energy released by a 21 megaton thermonuclear weapon. This equation tells us the total energy budget available to a computer of mass m. The second equation: the Heisenberg uncertainty principle in its energy-time form, delta E times delta T, is greater than or equal to h bar over 2. Delta E is the uncertainty in energy. Delta T is the uncertainty in time, the minimum time required for the system to change state. Werner Heisenberg, born 1901, died 1976, German physicist, Nobel Prize 1932, formulated this principle in 1927. The uncertainty principle is not a limitation of our measuring instruments. It is a fundamental property of quantum mechanics, a consequence of the wave nature of matter, of the non-commutation of energy and time operators, of the mathematical structure of quantum theory itself. The uncertainty principle tells us the faster a system changes state, smaller delta T, the larger the energy uncertainty must be, larger delta E. Speed costs energy. Processing information faster requires more energy. The trade-off is absolute. The connection between these two equations, E equals mc squared, and delta E delta T greater than or equal to h bar over 2, produces the Bremermann limit. The mass-energy equivalence sets the total energy budget. The uncertainty principle sets the rate at which that budget can be spent on computation. The result is a speed limit that depends on nothing but the mass of the computer, the speed of light, and Planck's constant, 3 of the most fundamental constants in physics. Combining the two, if a computer of mass m uses its entire mass energy, E equals mc squared, for computation, the minimum time per bit operation is delta T equals h over E equals h over mc squared. The maximum rate of bit operations is therefore mc squared over h, which gives approximately 1.36 times 10 to the 50 bits per second per kilogram. This is the Bremermann limit. A 1 kilogram computer, the most efficient computer physically possible, using every atom, every subatomic particle as a processor, can flip at most 1.36 times 10 to the 50 bits per second. Let us ground this in concrete examples, working upward from familiar scales to cosmic ones. A modern laptop, mass approximately 2 kilograms, has a Bremermann limit of approximately 2.7 times 10 to the 50 operations per second. Its actual processing speed is approximately 10 to the 10 billion operations per second. The laptop operates at approximately 10 to the negative 40 of its theoretical maximum. The gap between current technology and the Bremermann limit spans 40 orders of magnitude. The Earth, mass approximately 5.97 times 10 to the 24 kilograms, approximately 1.32 times 10 to the 25 pounds, has a Bremermann limit of approximately 10 to the 75 operations per second. If the entire Earth were converted to a computer, every atom of iron, silicon, oxygen and nickel in the core, mantle and crust repurposed as a processor, it could perform at most 10 to the 75 operations per second. This is an incomprehensible number, but it is finite, and it is far less than what would be needed to simulate the universe. The Sun, mass approximately 1.989 times 10 to the 30 kilograms, approximately 4.385 times 10 to the 30 pounds, has a Bremermann limit of approximately 10 to the 80 operations per second. If the Sun, a sphere of hydrogen and helium plasma, 1.4 million kilometers in diameter, approximately 870,000 miles, burning at 15 million Kelvin in its core, were entirely converted to computation, it could process at most 10 to the 80 operations per second. The entire observable universe, approximately 1.46 times 10 to the 53 kilograms of baryonic matter, approximately 3.22 times 10 to the 53 pounds, has a Bremermann limit of approximately 10 to the 103 operations per second. If every atom in the observable universe, every hydrogen atom in every star, every helium nucleus in every gas cloud, every carbon atom in every planet, every iron atom in every white dwarf, were repurposed as a computational element, the total processing speed would be, at most, 10 to the 103 operations per second. The Margolus-Levitin theorem gives a more precise, more fundamental quantum speed limit. Norman Margolus, born 1953, American physicist at MIT, and Lev Levitin, born 1928, Russian physicist at Boston University, proved in 1998 that the minimum time for a quantum system with average energy E above the ground state to evolve to a distinguishable orthogonal state is delta T is greater than or equal to pi h bar over 2 E. This is not an approximation. It is a mathematical theorem, proved from the axioms of quantum mechanics, as rigorous as the Pythagorean theorem in geometry. The proof follows from the Schrödinger equation and the properties of unitary development in Hilbert space. No physical system, no quantum computer, no classical computer, no hypothetical future technology can violate it. It is an absolute, unconditional, universally applicable speed limit on computation. Equivalently, the maximum rate of elementary quantum operations is 2e over pi h bar operations per second. For a system with energy E, this is the fastest it can change state, period. The Margolus-Levitin theorem is slightly more restrictive than the Bremermann limit for some systems. It uses h bar rather than h, and includes a factor of pi. But both converge on the same conclusion. The computational speed of any physical system is bounded by its energy. More energy means faster computation. But more energy also means more mass by E equals mc squared, which means more gravitational effects, which means, at the limit, the system collapses into a black hole. The ultimate computer is a black hole. And even a black hole is bounded by the Bekenstein-Hawking entropy, the maximum information it can store. This is the part that stays with me. Not the sizes of the numbers, the absoluteness of the limits. These are not engineering challenges to be overcome by better technology. These are not barriers to be broken by future discoveries. These are consequences of the most fundamental laws of physics, quantum mechanics and relativity. If quantum mechanics is correct, the Margolus-Levitin theorem holds. If relativity is correct, the Bremermann limit holds. If general relativity is correct, the Bekenstein bound holds. To exceed these limits, you would need to violate quantum mechanics, relativity, or both. No experiment in the history of physics has ever violated either. Seth Lloyd, born approximately 1960, American physicist at MIT, professor of mechanical engineering and physics, applied all three limits to the entire observable universe in his 2000 paper, Ultimate Physical Limits to Computation, published in Nature. Lloyd asked, if the entire observable universe were a computer, if every particle were a processor, every interaction a calculation, every quantum degree of freedom a bit, what is the maximum amount of computation it could have performed in its entire history? The calculation proceeds as follows. The total mass energy of the observable universe is approximately E equals 5 × 10⁻�69 joules, including baryonic matter, dark matter, and the energy equivalent of the cosmological constant. The age of the universe is approximately T equals 4.35 × 10⁻17 seconds, 13.8 billion years. The maximum number of elementary operations the universe could have performed is n sub ops equals 2et over pi h bar, which gives approximately 10 to the 120 operations. 10 to the 120. This is the absolute maximum, the theoretical ceiling for the total computational work the observable universe could have performed in its entire 13.8 billion year history. Every particle interaction since the Big Bang, every nuclear reaction in every star, every photon absorption and emission, every gravitational deflection, every quantum fluctuation, all of it, the total computational output of the cosmos, amounts to at most 10 to the 120 elementary operations. The number of bits available for storage is bounded by the Bekenstein bound, approximately 10 to the 90 bits for baryonic matter, potentially up to 10 to the 120 bits if gravitational degrees of freedom, horizon bits, are included. Lloyd titled his thought experiment The Ultimate Laptop, a 1 kilogram, 1 liter computer operating at the Bremermann limit. The ultimate laptop performs approximately 10 to the 51 operations per second on approximately 10 to the 31 bits. It runs at a temperature of approximately 10 to the 9 Kelvin, a billion degrees, because the energy density required to reach the Bremermann limit is so high that the computer is effectively a thermonuclear plasma. This is not a laptop anyone could use. It is a thought experiment, designed to show what the laws of physics permit and what they prohibit. Think about that number, 10 to the 120 operations. This is the total computational capacity of the observable universe since the Big Bang. It is not the capacity of our computers, it is not the capacity of our technology, it is the capacity of the universe. All matter, all energy, all time, all space, every particle functioning as a processor. And it is finite. And it is insufficient to simulate the universe itself. Now consider what it would take to simulate the universe, and the specific quantifiable reasons why the calculations required exceed the universe itself. A simulation of the universe must track every degree of freedom of every physical system within it. The question is, how many degrees of freedom does the universe have? At the classical level, a system of n particles in 3 dimensions has 6n degrees of freedom, 3 position coordinates and 3 momentum coordinates per particle. For the approximately 10 to the 80 atoms in the observable universe, this gives approximately 6 times 10 to the 80 classical degrees of freedom. This is already a large number, but classical mechanics is not fundamental. The universe is quantum mechanical at its deepest level, and quantum mechanics makes the problem exponentially worse. At the quantum level, the state of a system with n distinguishable particles is described by a wave function in a Hilbert space whose dimension grows exponentially with n. For a system of n qubits, 2-level quantum systems, the Hilbert space has dimension 2 to the n. The wave function is a vector in this space, requiring 2 to the n complex amplitudes to describe completely. For n equals 10, the Hilbert space has 1024 dimensions. For n equals 100, the Hilbert space has approximately 10 to the 30 dimensions. For n equals 300, the Hilbert space has approximately 10 to the 90 dimensions, already matching the Bekenstein bound for the observable universe. For n equals the number of particles in the observable universe, approximately 10 to the 80, the Hilbert space has dimension 2 to the power of 10 to the 80. 2 to the power of 10 to the 80. Let us attempt to grasp this number, knowing that the attempt must fail. The logarithm of this number, the number of digits, is approximately 10 to the 80 times the logarithm of 2, which is approximately 3 times 10 to the 79. The number has approximately 3 times 10 to the 79 digits. To write it out, a 1 followed by 3 times 10 to the 79 zeros would require more digits than there are particles in the observable universe. The number is not merely large, it is categorically beyond physical reality. It exceeds every number that has physical meaning. It exceeds the Bekenstein bound for the observable universe, 10 to the 90 to 10 to the 120 bits, by a margin that is itself a number beyond comprehension. The memory required to store this wave function, even using 1 bit per dimension, is approximately 2 to the power of 10 to the 80 bits. This exceeds the Bekenstein bound for the entire observable universe by a factor with 10 to the 80 digits in its exponent. The simulation cannot fit inside the universe. the universe does not have enough information capacity to store the wave function of its own quantum state. This is not a technological limitation. It is a mathematical impossibility within the framework of physics. This analysis also assumes that the universe can be described by a finite-dimensional Hilbert space, which is itself an approximation. In quantum field theory, the Hilbert space of even a single quantum field on a continuous spacetime is infinite-dimensional. Discretizing spacetime at the Planck scale, the smallest meaningful scale where quantum gravitational effects become dominant, converts the continuous field to a lattice with a finite but extraordinarily large number of degrees of freedom. The Planck length, approximately 1.616 times 10 to the negative 35 meters, approximately 6.36 times 10 to the negative 34 inches, is the shortest distance at which our current understanding of physics applies. Below this scale, quantum gravitational effects, the interplay between quantum mechanics and general relativity, become dominant, and our current theories break down. Max Planck, born 1858, died 1947, German physicist, Nobel Prize 1918, the originator of quantum theory, derived these units in 1899 from three fundamental constants: h-bar, the quantum of action; g, Newton's gravitational constant; and c, the speed of light. The Planck length is the unique combination of these constants with dimensions of length. L sub p equals the square root of h bar g over c cubed. The Planck time, approximately 5.39 times 10 to the negative 44 seconds, is the Planck length divided by the speed of light. T sub p equals L sub p over c. These are not arbitrary units. They are the natural units of quantum gravity, the scales at which the quantum nature of space-time itself becomes dominant. To simulate the universe at Planck resolution, to track every degree of freedom at the finest meaningful scale, we would need to discretize space-time into cells of Planck volume. The Planck volume is L sub p cubed, approximately 4.22 times 10 to the negative 105 cubic meters. The observable universe has a volume of approximately 4 times 10 to the 80 cubic meters. The number of Planck volumes in the observable universe is therefore approximately 4 times 10 to the 80 divided by 4.22 times 10 to the negative 105, approximately 10 to the 185 Planck cells. Each cell has internal degrees of freedom. At a minimum, each point in space-time hosts the quantum fields of the Standard Model. 6 quark flavors, each in 3 colors, 8 gluon fields, the photon field, the W and Z boson fields, the Higgs field, 3 charged leptons, 3 neutrinos, dozens of independent field components at each point, each with its own quantum state. The total number of degrees of freedom is approximately 10 to the 185, multiplied by the number of field components per cell, conservatively 10 to the 187 or more. Alan Turing, born 1912, died 1954, British mathematician and logician, conceived the Turing machine in 1936, an abstract computational device that defines in principle what is computable. The Church-Turing thesis, proposed independently by Alonzo Church and Turing, states that any function computable by an algorithm can be computed by a Turing machine. Turing showed that any problem solvable by an effective procedure can be solved by a Turing machine, and that some problems, the halting problem, are fundamentally unsolvable. Turing's work established the theoretical limits of computation from the logical side. The Bekenstein bound, the Bremermann limit, and the Margolus-Levitin theorem established the limits from the physical side. Together, they define the boundary of what is computable in the physical universe. And the simulation of the universe falls far beyond that boundary. The computational cost of evolving this state for one Planck time step, performing one elementary operation on each degree of freedom, is approximately 10 to the 185 operations. The total number of Planck time steps in the age of the universe is approximately 4.35 times 10 to the 17 seconds, divided by 5.39 times 10 to the negative 44 seconds, approximately 8 times 10 to the 60 steps. The total operations required is approximately 10 to the 185 times 8 times 10 to the 60, approximately 10 to the 246 operations. 10 to the 246. The universe has performed at most 10 to the 120. The deficit is 10 to the 126, a factor with 126 digits. The simulation exceeds the universe's capacity by 126 orders of magnitude. This is also a conservative estimate. It assumes one operation per Planck cell per Planck time. In practice, quantum field theory requires interactions between neighboring cells, nearest neighbor coupling in lattice gauge theory, which multiplies the computational cost by a factor proportional to the number of neighbors. It assumes the minimum number of degrees of freedom per cell. Real QCD alone has 8 gluon fields times 3 color charges times 6 quark flavors per lattice site, a complexity that makes even toy lattice simulations extraordinarily expensive. This brings us to quantum chromodynamics, QCD, and to the specific, concrete, experimentally confirmed difficulty of simulating even small quantum systems in practice. QCD is the theory of the strong nuclear force, the force that binds quarks into protons and neutrons, and binds protons and neutrons into atomic nuclei. Without the strong force, there would be no nuclei, no atoms beyond hydrogen, no chemistry, no stars, no planets, no complexity of any kind. QCD is described mathematically by the gauge group SU3, a non-abelian gauge theory, meaning the force carriers, gluons, carry color charge themselves and interact with each other. This self-interaction produces extraordinarily complex non-linear dynamics that make QCD qualitatively different from quantum electrodynamics, QED. In QED, the theory of the electromagnetic force, the coupling constant, the fine structure constant alpha, approximately 1/137, is small. This allows physicists to calculate electromagnetic processes using perturbation theory, expanding the answer as a power series in alpha, where each successive term is smaller than the last by a factor of approximately 1/137. The series converges quickly, and the first few terms give extraordinarily accurate predictions. The anomalous magnetic moment of the electron is predicted by QED to 12 decimal places, matching experiment. In QCD, the coupling constant at low energies is of order 1, not small. Perturbation theory fails. The power series does not converge. Each term is as large as the last. Alternative methods are required. The standard computational approach is lattice QCD, a method invented by Kenneth Wilson in 1974 that discretizes space-time into a four-dimensional grid and uses Monte Carlo techniques to numerically evaluate the path integral. Lattice QCD has achieved striking successes. It has correctly predicted the masses of hadrons, protons, neutrons, pions, kaons, and more exotic particles to within a few percent, and it has provided the strongest evidence that QCD is the correct theory of the strong force. Lattice QCD, however, faces a fundamental computational barrier for real-time dynamical processes: the sign problem. In Euclidean lattice QCD, the standard approach, the path integral is evaluated in imaginary time, a mathematical trick that converts the oscillating integrand of quantum mechanics into a positive, exponentially decaying integrand suitable for Monte Carlo sampling. But real-time dynamics, such as the collision of two protons at the Large Hadron Collider, require Minkowski time, real time, where the integrand oscillates rapidly in sign. The oscillations cause catastrophic cancellations. Positive and negative contributions nearly cancel, leaving a tiny residual that is swamped by statistical noise. This is not a limitation of current algorithms. It is a mathematical obstruction, a consequence of the structure of quantum mechanics itself. No classical Monte Carlo method can efficiently overcome the sign problem for general real-time QCD processes. Richard Feynman, born 1918, died 1988, American physicist at Caltech, Nobel Prize 1965, one of the creators of quantum electrodynamics, recognized this problem in a seminal 1982 lecture at MIT. Feynman argued that simulating quantum systems on classical computers is fundamentally inefficient, that the computational cost grows exponentially with the size of the quantum system. His proposed solution was quantum simulation, using quantum systems to simulate other quantum systems. Feynman stated, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy." Feynman's insight launched the field of quantum computing. David Deutsch, born 1953, British physicist at Oxford, formalized the concept in 1985 with the quantum Church-Turing-Deutsch principle. A universal quantum computer can simulate any physical process with at most polynomial overhead. This means quantum computers can simulate quantum systems exponentially faster than classical computers, reducing the cost from exponential to polynomial in the system size. This is an enormous improvement. But polynomial does not mean small, and polynomial overhead is still constrained by the Margolus-Levitin theorem and the Bekenstein bound. Quantum computers approach the fundamental limits more efficiently. They do not break them. In July 2024, IBM reported a milestone in quantum simulation of QCD-like dynamics. Using a 112-qubit processor called IBM_Torino, IBM's team simulated a simplified model of hadron dynamics, a one-dimensional approximation of QCD known as the Schwinger model, quantum electrodynamics in one spatial dimension, which shares key features with QCD, including confinement and pair production. The quantum circuit used 13,858 C0 gates, 2-qubit entangling gates, with a circuit depth of 370 layers. The team applied aggressive error mitigation techniques, Pauli twirling, zero-noise extrapolation, to extract meaningful results from noisy hardware. These quantum error correction protocols are essential for maintaining coherence in such complex calculations. The result was notable. It demonstrated that current quantum hardware, despite high error rates and limited qubit counts, can produce meaningful physics results for simplified models when combined with sophisticated classical post-processing. The team used a technique called utility-scale quantum computing, leveraging the quantum processor not as a perfect simulator, but as a noisy sampling device whose outputs, corrected by classical error mitigation algorithms, converge on the correct physics. This is a practical approach to near-term quantum advantage, working with the noise rather than eliminating it. The limitations, however, are equally notable and directly relevant to our thesis. The simulation was one-dimensional. Real QCD operates in 3 spatial dimensions plus time. It used a simplified model, the Schwinger model, which is quantum electrodynamics in one spatial dimension, sharing features with QCD like confinement and pair production, but lacking the full complexity of 3 color charges and 8 gluon species. The 112 qubits simulated a handful of lattice sites, with a limited number of time steps. A realistic 3-dimensional lattice QCD simulation with physical quark masses, full gluon dynamics, and sufficient volume to accommodate hadronic bound states would require millions or billions of qubits, with error rates orders of magnitude lower than any current or near-term device. The gap between IBM's 2024 milestone and a full QCD simulation is not a gap that Moore's law will close. It is a gap measured by the fundamental computational limits we have examined: the Bekenstein bound, the Bremermann limit, the Margolus-Levitin theorem. Consider the scale of the challenge. In 2019, Google announced a milestone in quantum computing. Their 53-qubit Sycamore processor performed a specific computational task, random circuit sampling, in approximately 200 seconds. A task that Google claimed would take the most powerful classical supercomputer approximately 10,000 years. This was hailed as quantum supremacy, the first demonstration that a quantum computer could outperform any classical computer for a specific task. The result was published in Nature and received global attention. The achievement was real. It was also extraordinarily modest in the context of our topic. The task, random circuit sampling, was a toy problem with no practical application. the 53 qubits simulated nothing physical. The computation lasted 200 seconds and produced a statistical distribution. This is the frontier of quantum computing in practice. 53 qubits performing a single specific task. The computational cost of simulating the full quantum state of the strong nuclear force in 3 dimensions requires resources that exceed 53 qubits by a margin comparable to the difference between a grain of sand and the observable universe. Consider another concrete grounding of scale. The Voyager 1 spacecraft, launched by NASA in 1977, still transmitting data, crossed the heliopause into interstellar space in 2012, after 35 years of travel. Its distance from Earth is approximately 163 astronomical units as of 2024, approximately 2.4 times 10 to the 13 meters, approximately 1.5 times 10 to the 10 miles. This is the farthest any human-made object has traveled. It is approximately 0.0006 light-years from Earth. The observable universe has a radius of approximately 46.6 billion light-years. The ratio of Voyager's distance to the cosmic horizon is approximately 10 to the negative 13 orders of magnitude. Voyager has traversed a trillionth of the distance to the edge of the observable universe, in 47 years of continuous travel at approximately 17 kilometers per second. Now scale the computational challenge the same way. The most powerful supercomputer on Earth, as of 2024, the Frontier system at Oak Ridge National Laboratory, capable of approximately 1.2 exaflops, 1.2 times 10 to the 18 floating point operations per second, performs approximately 10 to the 18 operations per second. The Bremermann limit for the entire observable universe is approximately 10 to the 103 operations per second. The ratio is approximately 10 to the negative 85. The world's most powerful computer operates at approximately 10 to the negative 85 of the universe's theoretical maximum. The gap is 85 orders of magnitude. To close this gap would require not merely better engineering, but converting the entire observable universe into a computer. Every particle, every quantum of energy, every degree of freedom repurposed for computation. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, a 27-kilometer, approximately 17-mile ring straddling the French-Swiss border near Geneva, operating at energies up to 13 TeV since 2015, collides protons at rates of approximately 1 billion collisions per second. The Higgs boson, discovered at the LHC in July 2012 by the ATLAS and CMS experiments, with a mass of approximately 125 giga-electron volts, approximately 133 times the proton mass, confirmed the existence of the Higgs field and the mechanism by which particles acquire mass. The discovery required analyzing approximately 1 quadrillion, 10 to the 15, proton-proton collisions over several years. Each of these collisions involves the strong force in full three-dimensional, dynamical, non-linear glory, quarks scattering, gluons self-interacting, particle-antiparticle pairs materializing from the vacuum, jets of hadrons spraying outward in cones of colored particles. A single proton-proton collision at the LHC involves physics that current lattice QCD cannot fully simulate from first principles. The LHC produces approximately 1 billion collisions per second. The computational cost of simulating even 1 second of LHC physics from first principles, tracking every quantum degree of freedom in every collision, exceeds the capacity of any computer that obeys the laws of physics. Before I continue, consider what this means. Take a moment. The most advanced quantum computer in the world, IBM's IBM_Torino, with 112 qubits and sophisticated error mitigation, can barely simulate a toy, one-dimensional approximation of the strong nuclear force using a circuit with 13,858 gates. The real strong force operates in 3 spatial dimensions, with 3 colors of charge, with 8 types of gluons, with quarks of 6 flavors, at energy scales spanning 15 orders of magnitude, from nuclear binding energies to LHC collision energies. The computational cost of a full, first-principles simulation of even a single proton-proton collision at the LHC is beyond the capacity of any computer that obeys the laws of physics, classical or quantum. And that is 1 collision, in 1 accelerator, on 1 planet, in 1 solar system, in 1 galaxy, among approximately 2 trillion galaxies in the observable universe. The simulation hypothesis proposes that the entire universe, 10 to the 80 particles, 10 to the 90 bits, 10 to the 120 operations of total history, is a simulation running on a computer. The physics says the computer required for this simulation exceeds the universe itself. The calculations required exceed the calculations the universe has performed. The memory required exceeds the memory the universe contains. The simulation cannot fit inside the universe. And if it runs outside the universe on some external computational substrate, then we are no longer talking about physics. We are talking about something beyond the physical. We are talking about a designer. This brings us to the simulation hypothesis, and to the specific, precise ways in which it fails when confronted with the physics we have examined. The simulation hypothesis has a longer history than most people realize. Konrad Zuse, born 1910, died 1995, German civil engineer and computer pioneer who built the world's first programmable computer, the Z3, in 1941, proposed in 1969 that the universe is a vast cellular automaton, a grid of simple computing elements whose interactions, following local rules, generate all of physical reality. Zuse's rechnende Raum, computing space, was the first serious proposal of digital physics. The idea that physical reality is, at its foundation, computational. Edward Fredkin, born 1934, American physicist and computer scientist at MIT, extended this idea in the 1980s and 1990s, arguing that information is more fundamental than matter and energy, and that the laws of physics are algorithms running on a discrete substrate. John Wheeler's It from Bit, the proposal that physical reality derives from information, can be seen as a philosophical version of the same idea. The modern simulation hypothesis was formalized by Nick Bostrom, born 1973, Swedish philosopher at the University of Oxford, in his 2003 paper, "Are You Living in a Computer Simulation?" Bostrom framed the argument as a trilemma, three mutually exclusive propositions, at least one of which must be true. First, almost all civilizations at our level of development go extinct before reaching the technological maturity to run detailed simulations of their ancestors. Second, among civilizations that do reach technological maturity, almost none choose to run such simulations. Third, we are almost certainly living in a computer simulation. The argument is probabilistic. If technologically mature civilizations can and do run many detailed simulations of past civilizations, then the number of simulated beings vastly exceeds the number of real beings. If you cannot tell from the inside whether you are simulated or real, and if simulated beings vastly outnumber real beings, then you are, by probability alone, almost certainly simulated. The argument has attracted attention from prominent figures. Elon Musk stated in 2016 that the odds of our living in base reality are 1 in billions. Neil deGrasse Tyson has entertained the idea as plausible. The simulation hypothesis has become a cultural phenomenon, featured in films, podcasts, and popular science books. Let us apply the prosecution after defense model with full rigor. The defense. The simulation hypothesis is logically structured. It does not claim we definitely live in a simulation. It claims that if advanced civilizations can simulate conscious beings in sufficient numbers, then most conscious beings are simulated, and we are probably among them. The argument follows from basic probability theory applied to large populations. The cross-examination. The argument rests on a critical assumption that computation can, in principle, simulate physical reality to arbitrary precision. This assumption, examined in light of the Bekenstein bound, the Bremermann limit, and the Margolus-Levitin theorem, fails. A simulation of the universe requires a computer with more information capacity than the universe contains, by the Bekenstein bound. It requires a computer that performs more operations than the universe has performed, by the Margolus-Levitin theorem applied to Lloyd's calculation. It requires resolving quantum degrees of freedom whose number grows What about the simulator's universe? Is it also simulated? By what? The chain of simulations must either extend infinitely, which is logically problematic. An infinite chain of dependent simulators never reaches a foundation, or terminate at a base reality, an unsimulated, uncaused, self-sufficient foundation. And the question becomes, what is that foundation? An unconscious computational substrate, mindlessly generating simulated universes with no purpose? Or an intelligent, knowing, willing creator who designed the simulation, including its extraordinarily fine-tuned physical constants, its elegant mathematical laws, and its capacity to produce conscious beings who can discover the computational limits of their own reality. In October 2025, physicists Mir Faisal and Lawrence Krauss, along with their colleagues, published a paper in the Journal of Holography Applications in Physics, arguing mathematically that the universe cannot be a computer simulation. Their central argument: computation is not more fundamental than space-time. Computation occurs within space-time. It requires physical substrates, matter and energy, physical resources, time and space, and is subject to physical laws, the Bekenstein bound, the Margolus-Levitin theorem, Landauer's principle, the second law of thermodynamics. A computer is a physical system. A simulation is a physical process. Neither can exist independently of the physical laws that govern them. The simulation hypothesis assumes that computation is more fundamental than the reality it simulates, that the code is primary and the physics is secondary. Faizal and Krauss argued that this assumption inverts the actual relationship. Physics constrains computation, not the other way around. A simulated universe is logically impossible within physics as we understand it, because the simulation would require computational resources exceeding the physical universe, which is, by definition, all the physical resources that exist. The verdict: the simulation hypothesis fails for three independent reasons. First, the computational resources required to simulate the universe exceed the universe's own capacity. Bekenstein, Bremermann, Margolus-Levitin, Lloyd. Second, the infinite regress of simulators has no physical foundation. Third, the 2025 Faizal-Krauss argument establishes that computation is not more fundamental than space-time, that a simulated universe inverts the actual dependence of computation on physics. The simulation hypothesis does not eliminate the need for a creator. It repackages the creator as a programmer. And the repackaging fails because the programmer must transcend the very physics that defines computation. This brings us to the related but distinct idea of digital physics. The proposal, championed by Zuser, Fredkin, and, in a more cautious form, Wheeler, that the universe is fundamentally computational. Digital physics proposes that space-time is discrete, that physical laws are algorithms, and that the development of the universe is a computation performed on an informational substrate. Digital physics is an interesting idea, but it faces serious problems. First, the empirical evidence for space-time discreteness is zero. No experiment has detected a discrete structure at the Planck scale. Lorentz invariance, the symmetry underlying special relativity, has been tested to extraordinarily high precision and shows no signs of the violations that most discrete space-time models predict. Second, if the universe is a computation, the question, what computer is running it, arises immediately, and we are back to the simulation hypothesis with all its problems. Third, and most fundamentally, even if the universe is computational, this does not explain why the computation has its specific structure. Why these algorithms? Why these initial conditions? Why these constants? The computational framing does not eliminate the need for an explanation. It restates the question in different language. When I first understood this, that the computational limits derived from the most fundamental physics render the universe unsimulable by itself, that the calculations required exceed the calculations the universe has performed, that the information required exceeds the information the universe contains, The simulation hypothesis, which I had found intellectually appealing in its secular framing, collapsed. Not because of a philosophical argument, because of the mathematics. The Bekenstein bound, the Margolus-Levitin theorem, Lloyd's calculation, the exponential growth of Hilbert space, the sign problem in QCD. The physics is not ambiguous. The universe cannot simulate itself, and anything capable of simulating it must transcend it. This brings us to the deeper question, the question that computational physics raises but cannot answer. Why does the universe have this specific computational structure? Why are the laws mathematical? Why are the constants fine-tuned? Why is information bounded by elegant equations? Why does a universe exist at all? And why this particular universe? The fine-tuning of physical constants is one of the most striking features of the universe, acknowledged by theists and atheists alike, celebrated and lamented, explained by no one. The fine structure constant, alpha, is approximately 1/137.036. This dimensionless number determines the strength of the electromagnetic interaction, the force that holds electrons in atoms, that governs chemistry, that makes molecules possible. Richard Feynman called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. If alpha were a few percent larger, electron orbitals would be too tightly bound for complex chemistry. If alpha were a few percent smaller, atoms would not form stable bonds. The value is not derived from any deeper principle. It is measured. It is what it is. And the question, why this value, has no answer within physics. The cosmological constant, lambda, is approximately 10 to the negative 122 in natural Planck units. This is the energy density of empty space, the dark energy, driving the accelerating expansion of the universe. The natural value predicted by quantum field theory, the sum of zero-point energies of all quantum fields, is approximately 10 to the 120 times larger. The discrepancy between the predicted and observed values, 120 orders of magnitude, is the largest disagreement between theory and observation in the history of physics. Sean Carroll has called this the biggest crisis in physics. Steven Weinberg used the anthropic principle to predict the order of magnitude of lambda before it was measured. But the anthropic principle is not an explanation. It is a selection criterion, applied within a multiverse framework that has zero observational evidence. If the cosmological constant were significantly larger, even by a factor of 10 or 100, the expansion of the universe would have been too rapid for galaxies, stars, and planets to form. Matter would have been dispersed before gravitational collapse could produce structure. If lambda were negative, the universe would have recollapsed before complexity could arise. The observed value is in a narrow window, a window whose width, compared to the natural range of possible values, is approximately 10 to the negative 120. This is not merely unlikely. By any rational assessment, it demands explanation. The strong nuclear force coupling, alpha sub s, is approximately 0.12 at the energy scale of the Z boson mass.
If the strong force were approximately 2% weaker, protons could not bind together to form nuclei.
No elements beyond hydrogen would exist. No carbon, no oxygen, no chemistry, no stars beyond the simplest hydrogen-burning dwarfs. If the strong force were approximately 0.5% stronger, the diproton, two protons bound together, would be stable, and nuclear reactions in stars would proceed so rapidly that hydrogen would be consumed in seconds rather than billions of years. No long-lived stars, no stable energy sources, no planetary environments in which complexity could develop. The ratio of electromagnetic to gravitational force strength is approximately 10 to the 36. Martin Rees, born 1942, British cosmologist, astronomer royal, former president of the Royal Society, identified this as one of his just 6 numbers. If this ratio were significantly smaller, stars would be smaller, dimmer, and shorter-lived. If it were significantly larger, no stars would form at all. The value determines the sizes and lifetimes of stars, which determine the time available for complexity to arise. Roger Penrose, born 1931, British mathematician, Nobel Prize 2020, calculated the probability of the Big Bang's initial conditions occurring by chance at approximately 1 in 10 to the power of 10 to the 123. This calculation specifically addresses the gravitational degrees of freedom, the Weyl curvature tensor, which was extraordinarily close to 0 at the Big Bang, smooth space-time, no gravitational clumping. The low Weyl curvature is what permits the arrow of time, structure formation, and the thermodynamic gradient from which all complexity derives. Paul Davies, born 1946, British-Australian physicist and cosmologist, recipient of the Templeton Prize, wrote that the odds against getting a life-permitting universe out of random numbers are so huge that one might suspect something more than chance. Davies has stated that cosmic coincidences seem to defy rational explanation, and that the universe appears to have been configured with extraordinary precision. Think about these numbers. Take a moment. The fine structure constant, 1 over 137. The cosmological constant, 10 to the negative 122. The strong force coupling, tuned to within 2%. The electromagnetic gravitational ratio, 10 to the 36. Penrose's initial conditions, 1 in 10 to the power of 10 to the 123. Each of these values is measured, not derived. Each could have been different. Each falls within a narrow range that permits atoms, chemistry, stars, complexity, and conscious beings. The probability of all of them falling within their life-permitting ranges simultaneously, by chance, is not merely small, it is effectively 0. What would you conclude from this evidence if you followed it honestly? The materialist response is the multiverse, an infinite ensemble of universes with different constants, in which we observe life-friendly values because only they permit observers. The anthropic principle applied across an infinite landscape of possibilities. Let us examine this. The multiverse has 0 observational evidence. No other universe has been observed, measured, detected, or interacted with. The theory is
unfalsifiable. No possible observation could prove it wrong. By the standards of the scientific method, observation, experimentation, falsifiability, reproducibility, the multiverse is not science. It is philosophical speculation dressed in mathematical language. The multiverse, however, does not solve the fine-tuning problem. It shifts it up one level. The multiverse generating mechanism, whatever inflaton field, whatever string landscape,
Whatever mathematical structure produces the ensemble of universes must itself have specific properties. It must obey specific laws. It must have specific parameters that permit the generation of universes with varying constants. Where do these meta laws come from? What fine-tuned the fine-tuner? The multiverse does not eliminate the need for explanation. It multiplies it. The Borde-Guth-Vilenkin theorem, proved in 2003, establishes that any space-time region with average expansion rate greater than 0 must be past incomplete. Even eternal inflation had a beginning. Even the multiverse had a first moment. The escape through infinite regression is closed. Science will eventually explain it is not an argument. It is a statement of faith. Faith in future discoveries deployed to avoid a present conclusion. Some questions are not scientific questions. Science operates within a framework of laws, using those laws to deduce consequences. Science cannot explain why the framework exists. No equation within physics explains why equations hold. No law within physics explains why laws exist. The question of why the universe has its specific computational structure, why the Bekenstein bound has its specific form, why the Margolus-Levitin theorem has its specific constant, why the fine structure constant is 1/137 and not some other value, is a question about the existence of the framework. And no framework can explain its own existence. The consciousness argument is directly relevant to our topic. The universe contains conscious beings, beings who can discover the Bekenstein bound, who can prove the Margolus-Levitin theorem, who can calculate Lloyd's limits, who can ask whether they are simulated. Consciousness exists. Atoms have no awareness. Molecules have no thoughts. No arrangement of unconscious particles has been shown to produce subjective experience. David Chalmers, Australian philosopher, identified this as the hard problem of consciousness. The problem of explaining why physical processes give rise to subjective experience. The hard problem remains unsolved. Neuroscience can correlate brain activity with conscious states. It cannot explain how electrochemical signals become the experience of seeing red, hearing music, or understanding a mathematical proof. If the universe is fundamentally informational, as Wheeler proposed, as the Bekenstein bound suggests, as the information theoretic limits confirm, then consciousness is an entity that processes, interprets, and is aware of information. The existence of such an entity in a universe of unconscious information processing particles, particles that obey the Bekenstein bound, that are limited by the Margolus-Levitin theorem, that process information at rates bounded by the Bremermann limit, demands an explanation that materialism cannot provide. Unconscious computation does not produce consciousness. Unconscious information does not produce awareness. The gap between the computational universe and the conscious mind is the gap between description and understanding, and materialism has no bridge. Now let us follow the evidence where it leads, and state the conclusion the evidence demands. Something has always existed. If there were ever truly nothing, absolute nothing, with no energy, no matter, no information, no computational substrate, no laws, no mathematical structures, then nothing would exist now. Nothing has no capacity. Nothing has no mechanism. 0 plus 0 equals 0. But we exist. The universe exists. 10 to the 80 particles process information at rates bounded by the Margolus-Levitin theorem. 10 to the 90 bits encode the state of a cosmos whose computational structure is governed by the Bekenstein bound. The fine structure constant is 1 over 137. The cosmological constant is 10 to the negative 122. Penrose's number is 1 in 10 to the power of 10 to the 123. Something has always existed. The universe itself has not always existed. The Big Bang, confirmed by the cosmic microwave background, the observed expansion, primordial nucleosynthesis, and the BGV theorem, establishes a finite past. The second law of thermodynamics confirms it. An infinite past would have produced heat death. The universe is not in heat death. The past is finite. Whatever caused the universe must be external to it, external to the computational limits that govern the physical cosmos. The cause is not bounded by the Bekenstein bound, because the Bekenstein bound applies to regions within the universe. The cause is not limited by the Margolus-Levitin theorem, because the theorem applies to physical systems with finite energy within space-time. The cause is not subject to the Bremermann limit, because the limit applies to masses within the physical universe. The cause transcends the computational structure it created, just as a programmer transcends the program, just as a mathematician transcends the equations. The evidence demands specific attributes. Power sufficient to bring a universe into existence with approximately 10 to the 70 joules of mass energy, with 10 to the 80 particles, with 10 to the 90 bits of information capacity. Knowledge sufficient to configure the physical constants. Alpha equals 1 over 137. Lambda equals 10 to the negative 122. Strong force tuned to within 2%. Penrose's initial conditions at 1 in 10 to the power of 10 to the 123, with precision that exceeds any probability threshold for chance. Will, because specific values were selected from among vast spaces of alternatives. Selection requires a chooser. Configuration requires a configurer. These are the attributes of a creator: power, knowledge, will, eternality, transcendence of the physical computational limits that govern every system within the created order. Not a programmer within the universe. The universe cannot contain its own simulator. Not a hypothetical post-human civilization. no civilization bounded by the Margolus-Levitin theorem can exceed the universe's computational capacity. A creator who exists outside the computational limits, outside the Bekenstein bound, outside the Margolus-Levitin theorem, outside the physical laws, and who configured those limits, those bounds, those laws with the precision that physics measures and cannot explain. Now let us step back and consider what we have examined, not as a list, but as a single converging argument that begins with the physical nature of information and ends with the attributes of whatever configured the universe's computational structure. We began with the discovery that information is physical. Shannon's 1948 information entropy, H equals the negative sum of P sub I times log base 2 of P sub I, quantified information in bits. Landauer's 1961 principle, erasing one bit costs at least K sub B T ln 2 in heat, showed that information processing is a thermodynamic process with a measurable physical cost. Bennett's work on reversible computation showed that the cost comes specifically from erasure, from the destruction of information. And Wheeler's it from bit proposed that information is not layered on top of physics, but is the foundation of physics. Every particle, every force, every physical event is, at its deepest level, an answer to a yes or no question. Information is physical. Computation is physical. And both are bounded by the laws that govern the physical universe. We examined the Bekenstein bound, Jacob Bekenstein's 1981 derivation establishing the maximum information content of any finite region as S less than or equal to 2 pi k sub b Re over h bar c. We showed that this bound is saturated by black holes, the Bekenstein-Hawking entropy, S sub bh equals A over 4 in Planck units, and that the observable universe contains at most approximately 10 to the 90 to 10 to the 120 bits. This is finite, it is calculable, and it sets an absolute limit on the memory available for any simulation, including the universe's simulation of itself. We examined the Bremermann limit, Hans Bremermann's 1962 derivation from E equals mc squared, and the Heisenberg uncertainty principle, establishing the maximum computational speed at approximately 1.36 times 10 to the 50 bits per second per kilogram. We showed that the Earth's Bremermann limit is approximately 10 to the 75 operations per second, and the observable universe's is approximately 10 to the 103 operations per second. We walked through the derivation step by step. Einstein's mass-energy equivalence provides the energy budget, and Heisenberg's uncertainty principle provides the time-energy trade-off. Speed costs energy, and energy is finite. We examined the Margolus-Levitin theorem, the 1998 proof establishing the quantum speed limit at delta t greater than or equal to pi h bar over 2e, or equivalently, a maximum of 2e over pi h bar operations per second. We showed that this theorem is a mathematical consequence of quantum mechanics, as rigorous as the Pythagorean theorem, and that no physical system can violate it. Quantum computers approach this limit more efficiently than classical computers. They do not exceed it. we examine Seth Lloyd's 2000 calculation, the ultimate physical limits to computation, showing that the observable universe, treated as the most powerful computer possible, could have performed at most 10 to the 120 operations on 10 to the 90 bits in its 13.8 billion year history. We showed that this is the absolute ceiling for the computational capacity of the cosmos, and that simulating the universe requires computational resources that exceed this ceiling by margins measured in hundreds of orders of magnitude. We examined the specific case of quantum chromodynamics, the theory of the strong nuclear force. We showed that QCD's nonlinear, strongly coupled dynamics make it computationally intractable for real-time simulations on classical computers, the sign problem. We described Feynman's 1982 insight that quantum simulation is the natural approach, and David Deutsch's 1985 formalization of the quantum Church-Turing-Deutsch principle. We described IBM's 2024 quantum simulation milestone, 112 qubits, 13,858 CNOT gates, circuit depth 370, and showed that it simulated a one-dimensional toy model, not the real three-dimensional strong force. The gap between current capability and full QCD simulation is not a technological gap. It is a gap measured by the laws of physics. We examined the simulation hypothesis, Nick Bostrom's 2003 argument, its cultural influence through Musk and others, and the 2025 Faizal-Krauss paper arguing that the universe cannot be a simulation. We showed that the simulation hypothesis fails because the computational resources required exceed the universe itself by the Bekenstein bound, the Margolus-Levitin theorem, and Lloyd's calculation, because the infinite regress of simulators has no physical foundation, and because computation is not more fundamental than space-time, but embedded within it. We examined digital physics, the proposal by Zuse, Fredkin, and Wheeler that the universe is fundamentally computational, and showed that even if this is true, it does not explain why the computation has its specific structure, its specific constants, its specific initial conditions. We examined the fine-tuning of physical constants, the fine structure constant at 1/137, the cosmological constant at 10 to the negative 122, the strong force coupling tuned to within 2%, Penrose's initial conditions at 1 in 10 to the power of 10 to the 123, and showed that these values are measured, not derived, that each falls within a narrow, life-permitting range, and that the probability of all of them occurring by chance is effectively zero. We examined the multiverse and showed that it has zero evidence, is unfalsifiable, does not eliminate fine-tuning but pushes it up one level, and is past incomplete by the BGV theorem. We examined science will explain it and showed that it is faith, not argument. Science operates within a framework. It cannot explain the framework's existence. No equation explains why equations hold. We examined consciousness and showed that the hard problem remains unsolved. Unconscious computation does not produce awareness. The information processing universe contains conscious beings who can discover its computational limits, and materialism cannot explain why. Every line of evidence we have examined, from Shannon's information theory to the Bekenstein bound, from the Bremermann limit to the Margolus-Levitin theorem, from Lloyd's ultimate computer to IBM's 112-qubit quantum simulation, from the sign problem in QCD to the simulation hypothesis's failure, from the fine-tuning of constants to the hard problem of consciousness, converges on the same conclusion. The universe has a specific, finite, bounded computational structure. That structure is governed by precise mathematical laws. Those laws are fine-tuned to permit complexity. The computational cost of simulating this structure exceeds the structure itself. And the question of why this specific structure exists is a question physics raises but cannot answer. The evidence points to an intelligent, powerful, eternal creator, one who exists outside the computational limits of the physical universe, outside the Bekenstein bound, outside the Margolus-Levitin theorem, outside the laws of thermodynamics. One who configured the laws with mathematical precision, set the constants with knowledge of the alternatives, and brought into existence a universe whose computational structure, from the Planck scale to the cosmic horizon, from the quantum no-cloning theorem to the Bekenstein-Hawking entropy, from Landauer's principle to the fine structure constant, testifies to the attributes of its maker. Power, knowledge, will, eternality, independence from the created order. The calculations required to simulate the universe exceed the universe itself. The computational capacity of the cosmos is finite, bounded, and insufficient for its own replication. The simulation hypothesis fails not because of technological limitations, but because of the laws of physics. And the laws of physics, the very laws that impose these limits, are themselves unexplained by physics. They are the framework within which computation occurs. They are not derived from computation. They are not generated by matter. They are not produced by energy. They are the specific, precise, fine-tuned configuration that permits everything else to exist. And that configuration demands a configurer. That is not faith against evidence. That is the conclusion the evidence demands when examined honestly. That conclusion, once reached, changes everything. Good night.